So I've been sent this definite integral problem, and it seemed as good as any. And I think the key with this is just to see a lot of examples. So let's do it. So let's see. This definite integral is from pi over 2 to pi of minus cosine squared of x times sine of x dx. So before we just chug through the math and do the antiderivatives and use the fundamental theorem of calculus to evaluate the definite integral, let's think about what we're even doing. So I've graphed this function right here, minus cosine squared of x times sine of x. And what we care about, we're finding the definite integral between pi over 2, which is roughly here. Let me see if I can make this a little bit bigger. So between pi over 2, which is right there, and between pi. So the definite integral of this function between here and here is essentially the area of the curve between the curve and the x-axis. And since the curve is below the x-axis here, this area is going to be a negative number. So that gives us immediately an intuition. We should be getting a negative number when we evaluate this. And just to prove, I actually typed it in up here. So let's now evaluate this definite integral. Now, I'll rearrange some of the terms here just to make it a little bit easier to read. But the way I always think about it is, well, let's see, I have a cosine and a sine. The cosine is squared, so all these crazy things are happening to it. So it seems like I could use substitution or the reverse chain rule somehow here. And what was the chain rule? The chain rule said if I took the derivative of f of g of x, that this is equal to f prime of g of x times g prime of x. That might completely confuse you, but I just wrote that here because, we could say, well, what if g of x is cosine of x? F prime of g of x is the cosine of x squared, and then the derivative of g of x, or the derivative of cosine of x, is sine of x. Or it's actually minus sine of x, and we have a minus sign here, so that works out well too. If this confuses you, ignore it. Well, essentially, we're just going to do the same thing, but we're going to do it with substitution. So let me do it with substitution. Let me erase this, if this confuses people. I want to do it however it is least confusing to you. Okay, let me erase that. Actually, let me do it with substitution, just because the way I was just doing is kind of my shortcut when I'm, back in the day when I was a mathlete. But it's good to be able to do it with substitution and helps you from making careless mistakes. So let me rewrite this first of all. This is the same thing as the integral from pi over 2 to pi of cosine squared of x. Actually, let me write that as cosine of x squared. Same thing, right? Times minus sine of x. Minus sine of x dx. And now it should be a little clearer to you. What's the derivative of cosine of x? It's minus sine of x. So I have a function, and it's being squared, and I have its derivative. So I can figure out its antiderivative by using substitution or the reverse chain rule. So let's make the substitution. U is equal to cosine of x. How did I know to substitute u is equal to cosine of x? Well, because I say, well, the derivative of this function is here. So when I find du, this whole thing is going to end up being du. And let me show that to you. So what is du dx? Du dx is equal to minus sine of x. That hopefully we've learned already. So what is du? If we multiply both sides by the differential d of x, we get du is equal to minus sine of x dx. So if we look at the original equation, this right here we just showed is equal to du. And this right here is what? Cosine of x is u. That was our original substitution. So we have u squared. U squared. So now let's take the integral. And I will arbitrarily switch colors. And now, this is a very important thing. If you're going to do substitution, if we're going to say u is equal to cosine of x, we're going to have to actually make the substitution on the boundaries. Or we could do the substitution, reverse the substitution, and then evaluate the boundaries. But let's do that. So if this is going from x is equal to pi over 2 to pi, what is u going from? Well, when x is equal to pi over 2, u is equal to cosine of pi over 2. Cosine of pi over 2, right? Because u is just cosine of x. And then when x is pi, u is going to be cosine of pi. Cosine of pi. And now the fun part. Cosine of x squared, well, that's just the same thing as u squared. And minus sine of x dx, that's the same thing as du. Did that here. Du. So this is equal to, so this is a pretty straightforward, and I'm just going to rewrite it. What's cosine of pi? Cosine of pi is minus 1. Cosine of pi over 2, well, that's 0. So we have the integral from u is equal to 0 to u is equal to negative 1 of u squared du. And now this seems like a simple problem. So this is equal to the antiderivative of u squared, which is fairly straightforward, u cubed over 3, right? You could just take the derivative of this, you get this. All I did is I increased this exponent to get the third, and then I divided by that exponent. And we're going to have to evaluate it at minus 1, and subtract from that, it evaluated at 0. And so this is equal to minus 1 to the third over 3, minus 0 over 3, and so this is equal to minus 1/3. And we are done. And if we look at this area from our original graph, what we just solved is we said the area of the curve between here and here is minus 1/3. Or if you wanted the absolute area, because you can't really have a negative area, it's 1/3, but we know it's negative because this curve is below the x-axis here. And that looks about right. That looks like about 1/3. I mean, if this cube right here is 1, then that looks about 1/3. So this is, the intuition all works out at least. So hopefully you found that vaguely useful. And actually, I just want to, actually, let me, since we have a little bit of time, hopefully you understood this. And if you did, don't worry about what I'm going to do now. But I want to show you how I tend to do it, where I just think of it as the reverse chain rule. And it's a little bit quicker sometimes. But it's really the same thing as what we just did with substitution. So if we erase all of this, and so if we have this integral right here, what I do is I say, well, I have cosine of x squared. Let me take this minus, well, I could use this one. I have cosine of x squared, and then I have minus sine of x. This is the derivative of this. Since the derivative is here, I can just treat this whole thing like an x term. So this is the same thing. So the antiderivative is cosine of x to the third over 3, and I evaluated it at pi and pi over 2. And remember, how did I do this? What allowed me to treat this cosine of x just like an x, or like a u when I did it with the substitution? Well, I had its derivative sitting right here, minus sine of x. So that's what gave me the license to just take the antiderivative, pretend like this cosine of x is just an x, is just a u, you could even say, and just say, take its exponent, raise it by 1, and divide it by 3, and then evaluate it from pi to pi over 2. So this is equal to cosine of pi cubed over 3 minus cosine of pi over 2 cubed over 3. This is minus 1 to the third. So this is equal to minus 1/3 minus this is 0. So we get the same answer. I just wanted to show you that. It's exactly the same with substitution. It's just I didn't formally do the substitution. But it's the exact same thing. Anyway, hope you found that helpful.